A very good afternoon to all. I hope you are all able to hear my voice. Is it audible?
Yes, sir.
Yes, sir.
Yes.
Okay, thank you. Yeah, I welcome all to another session on mobile communication and networks, Unit 1. So in the last class, we had seen introduction to mobile communications, the prerequisites required, the introduction to Unit 1, and some of the few concepts involved in Unit 1. So I'll give you a recap on that, and then I'll proceed on to the next topic. Okay, so the recap is that we had seen frequency reuse concept, the basic definitions in cellular systems, we had seen the basic definition of cellular systems, cellular concepts, frequency reuse, the channel capacity, the channel assignment strategies, the fixed channel, called as FCA, and the dynamic channel assignment, DCA. So now we are going to see an important concept in the cellular systems, which is handoff. So handoff occurs when a mobile moves into a different cell during a conversation. In the sense, there are two different cells adjacent to each other, having two different base stations. As in this diagram, you have like 3 clusters. Each cluster is having 7 cells, and when a mobile is moving from one cell, for example, I take F to A, from F to A, when it is moving during a call or during a conversation, what will happen is that F will have a base station, A will have a base station. So the mobile switching center will transfer the call to a new channel belonging to the new base station. So this is what we call as handoff. Leaving the older base station and moving on to the newer base station. So the process is being done by a mobile switching center, which transfers the call. So this handoff operation involves identifying new base station and allocation of voice and control signal to channels associated with new base stations. So this must be performed successfully, infrequently, and imperceptible to user, which should not cause any mishaps to the user. So to meet these requirements, an optimum signal level must be defined to initiate a handoff. So if the signal level falls below a threshold level, handoff will cut the call. Call cut will occur. So that's what we call as call dropping. The conversation will be disabled. So minimum usable signal for acceptable voice quality is in the range of -90 to minus decibel meter. So the voice quality should be always -90 to -100. So always a threshold value higher than this is being set for your handoff strategy. So this we call as handoff threshold level. So by looking into this diagram, you can able to see that we have a base station A, base station B. Here the mobile. See this car. This car is in motion. This car is moving, and it is having a mobile phone or a cellular phone where a call conversation is going on. So these are your time. So time at height 1, time at height 2, time at height 3, depending upon the base station. Okay. So the base station A, where the mobile is present, receives signals with a coverage in this form. It will cover like in this form. So this is your threshold. So this is your threshold 1. This is threshold 2. This is threshold 3. So if the signal goes beyond this L1 point, which is nearly TH2, so the call will get cut. If it is above this TH1, the call will be connected entirely during this time from base station 1 to base station, so base station A to base station B. I'll show you this animation in short while. Don't worry how a handoff occurs. So this is an illustration of the handoff scenario at the cell boundaries. You can see that this is one cell, base station 1. This is another cell, base station 2. A is labeled as cell 1. B is labeled as cell 2. So a mobile, you can see that a car carrying a mobile is moving from A to B. Okay, in this point. So here is the level. So received signal level during improper handoff situation will be like this. The call will drop. Diagram A, consider figure A. Improper handoff situation. So when it moves from this point to this point, from A point to B point, during a call, so it drops instantaneously and call gets dropped or call is terminated. So level at point A, handoff threshold is this point. Minimum acceptable signal to maintain the call is this point. So if it goes beyond this, the call gets terminated. So conversation gets disrupted. So in a proper handoff situation, what will happen is that, so it starts from here. You can see that level at point B. So the received signal level will be here. So level at which the handoff is made, the meaning is that minimum threshold is being maintained and handoff threshold is maintained. Call properly is being transferred from base station 1 to base station 2. So this is proper handoff situation. So this handoff strategy is an important concept in the design of a mobile communication, especially in cellulars. So handoff is made up of two strategies. One is call termination, which is what we had seen here in figure A, improper handoff situation. Another one is proper handoff situation. Okay. So handoff is made when a signal at the base station falls below a certain threshold. So during handoff, in order to avoid call termination of the conversation, safety margin should exist and it should not be too larger or too smaller. So that is what the threshold level. So the threshold level is calculated by power handoff minus the power minimal used or minimum usage. So handoff decides whether the call to continue during the transmission from A to B or not to continue. So in deciding when to hand off, it is important to ensure that the drop in the signal level is not due to momentary fading. Momentary fading is moment of the mobile's faded signals. In order to ensure this, base station to monitor the signal for a certain period of time before initiating a handoff. Always the length of the time needed to decide if handoff is necessary or not will depend only on the speed at which the mobile is moving. If the mobile is moving at a slower speed, the handoff strategy will work in better way. And if the mobile is moving in a very fast way, all may get terminated. In first generations of cellular system, the signal strength measured by the base stations and they were being supervised by the mobile switching centers. Signal strength, so which determines your handoff. So a spare or an additional receiver in the base station called locator receiver will monitor the receiver signal strength of RVCs in neighboring cells, which is receivers visiting center. So which tells that the mobile switching center about these mobiles and their channels, whether how much amount of signal strength is present, whether to terminate the call or whether to continue the call. All will be present in the base station. So this locator receiver will see if the signal to the base station is significant better than the host base station. So the mobile switching center will monitor all the received signal strength from all base stations and decides on handoff. In the second generation systems, we had mobile assisted handoffs, MAHO. So in MAHO, every mobile station will measure the received power from the surrounding base station, and continuously it will report all these values to the corresponding base stations. So with this, the signal strength of neighboring base stations can be easily measured. So as long as the mobile switching center no longer monitors the receiver signal strength of all the channels, it has reduced the computational load considerably since it monitors mobile switching center itself. It enabled much more rapid and efficient handoffs, and it became imperceptible to the user. Imperceptible in the sense, when the call gets terminated, what will happen is that the user or the customer will get angry. He would be in an important call, he would be in an important meeting or a conversation, or important information would have been exchanged. During that period, if a call gets cut, the user will be tremendously in pressure, or he will scold the network operator. So this we call as imperceptible to user. He cannot tolerate in that cases. So he has to move on to another network. So that can be avoided in the case if you use proper handoffing. So the handoff is divided into two, which is a soft handoff and a hard handoff. So in channelized wireless systems that assigns different radio channel during handoff, the spread spectrum of the mobile station shares the same channel in every cell, which we call as hard handoff. Sharing the same channel from one cell to another cell during the transmission from that cell to another cell. So we call it as hard handoff. And the ability to select between the instantaneous received signals from different base stations is called as soft handoff. So handling the channels within the same cell we call as hard handoff. With the different base stations we call as soft handoff. Next we have an inter-system handoff. So this is when if a mobile moves from one cellular system to a different cellular system, an inter-system handoff is necessary. In this case, what will happen is that a mobile switching center will engage in inter-system handoff when signal becomes weak in a given cell, and the mobile switching center cannot find another cell within its system to transfer the ongoing call. So this was probably during the year 2002, before 2004, 5 and 6. Before 2006 and 2007, this inter-system handoff played a major role, where the network operators were using unique base stations. So after 2006 or 2007, they came to an MOU such that they will share the base stations. So where this inter-system handoff came into play. So many issues was to be solved. The local call may become a long distance call. Compatibility between the two mobile switching centers was an issue in this inter-system handoff. Next is prioritizing handoffs. So the issue was is that perceived grade of service, which is a service quality as viewed by users. Quality in terms of dropped or blocked calls, which was not a voice quality. So assigning higher priority to a handoff versus a new call request. A dropped call becomes a blocked call. So these three were the GOS to be considered in prioritizing handoffs by the base stations. It is not by the user, it is by the base stations. So always the blocked calls or dropped calls has to be determined by the base station, and the base station has to decide whether I need to use handoff procedure to assign to a new channel user, or I need to go for an existing handoff strategy for the same user, depending upon the situations. So this was an issue. So for this, the guard channels were being introduced. The guard channels were the percentage of total available cell channels exclusively set aside for handoff requests. So this was done by making a fewer channels available for new call requests. Whenever new call comes, the channel size or the number of channels available for newer calls was very much lesser as compared to the existing calls during the transmission from point A to point B, or from point base station 1 to second point base station. So a good strategy is dynamic channel allocation. Depending upon the requirements during the moment of the mobiles or cellular phones, from one station to other station, one station to another station, dynamic channel allocation can be done rather than going for fixed allocations. So dynamic channel assignment can be used. The adjustment number of guard channels as needed by demand. So as the demand increases or as the demand decreases, depending upon the requirement, the adjustment of the channels can be done with low traffic. So next is queuing of handoff requests. Queuing in the sense following a strategy to address or to service the handoffs being made by the users during the transmission from cell 1 or cell 1 to cell 2, or from point A to point B. Why queuing is necessary is that in every scenario, one user will move from one base station to another base station. There would be n number of users moving in and out. So depending upon them, service is to be done. So the principle of queuing is to be adopted. So depending upon the time period. Okay. So this is being decided by the usage of time delay between handoff threshold and minimum usable signal level to place a blocked handoff request in queue. So a handoff request can keep trying during that time period instead of having a single block or no block decision. So the prioritized requests will be always done based upon the mobile speed of the mobile. If they are traveling at a higher speed from cell 1 to cell 2, or from point A to point B, there are 3 vehicles moving or 3 mobiles moving. One is at a lower speed, one is at an average speed, one is at a higher speed. So the prioritize will be given for a mobile which is moving at a higher speed, because that requires handoff urgently as compared to average and lower speed of mobile movement. Then after the mobile is going at a higher speed is being addressed, his request is made then to the average person or our people who is traveling with an average speed, then to the lower speed. So this is how prioritizing or queuing will. So there are some practical considerations to be done, or practical considerations in handoffs. One is pedestrian users. Pedestrians is the persons those who are walking. Okay. And vehicle users those who are moving in vehicles. Okay. Pedestrian. So depending upon this, the small cell size of the cell can be increased or decreased. The mobile switching center load is heavy, and high-speed users are passed between very small cells. So for this, the concept of umbrella cells is being introduced. Okay, umbrella. We see that also. So umbrella cells is that using different antenna heights and transmitting power levels to provide large and small cell coverage. I'll show you that in the diagram. So multiple antennas and transmitters can be co-located at single location if necessary. So larger cells will cover high-speed traffic with fewer handoffs. As I said, 3 types of people are moving from point A to point B. One person with higher speed, another person with lower speed, another person with average speed. So when the person is moving with a higher speed, he can go for a larger cell, or the mobile will switch on to a larger cell where high-speed traffic and fewer handoffs are being addressed. So when the average and the lower speed person is moving from point A to point B, you can use the smaller cell, or it will switch on to the smaller cell concepts with the low speed traffic. So the examples are interstate highway passing through a urban center, office, parks, or nearby shopping malls. This umbrella cells can be used. So high antenna towers can be used for large cell, low antenna towers can be used for small. So this is your umbrella cell concept. So the umbrella cell approach, we have a cell, the hexagonal shaped structures, and we have one base station. You can see that this base station is the height of this base station is higher. So this covers this entire large area. So large umbrella cell for high speed traffic in cover. So then we have small base stations. You can see that small 1, 2, 3, 4, 5 within this one cell. So which we call this as microcells. Okay, so small microcells will address, having these base stations will address the low speed movers or persons moving from one base station to another base station with in slow motion. So these small Small microcells are for low speed traffic. So you can see that this antenna, this base station antenna will cover the entire region as well as this region also. So this is in the shape of an umbrella. So hence the name umbrella cell. So these are the typical handoff parameters for first generation, second generation. The threshold margin was 6 to 12 decibels. And the total time taken was 8 to 10 seconds. The analog cellular system first generation. In digital cellular second generation, the total time to complete a handoff was reduced from 8 to 10 to 1 to 2 seconds, and the threshold margin was reduced from 6 to 12 decibels to 0 to 6 decibels. And these digital cellular systems were enabled by mobile assisted handoffs. MAHO. Then the reuse ratio for hexagonal cell reuse distance is given by D is equal to R square root of root 3 into N. So R is the cell size or cell radius and N is the cluster size. So if N increases, D also will increase. And the reuse factor can be calculated by Q is equal to D by R, which is equal to root 3 into N. So I'll start here in this. So any doubts in handoff? If you have any doubts in a handoff strategy, you can type in chat box, because the next topic that I'm going to proceed is a different topic, which you call as interference. Okay, since there are no queries, I move on to the next topic called as interference. What we are going to see in this interference is that two different interferences. One is co-channel interference, another one adjacent channel interference. And in this, we'll be seeing how to calculate this signal to interference ratio, SIR. Interference is a major limiting factor in the performance of cellular radio, which limits the capacity and increases the number of dropped calls. So the sources of interference includes a mobile in the same cell, or when a call is in progress in the neighboring cell, or the other base stations operating the same frequency band. So two different cells having the same frequency band. All this all causes interference. So let us see what happens if these all are present. So when interference is present in voice channels, it causes noises in the background. So when you make a call, a 2G call to your person, and if there is an interference, how you can judge is that unwanted noises will be in the background. Two persons will be conversating with each other, and unwanted disturbances will be arriving. That is one. Second one is the crosstalks. So, right from before 2010, okay, before the year 2010, you would have experienced these crosstalks in much of the operators, within the operators and in the operators also. So when a mobile call is made, or when a landline call is made from one mobile phone to another mobile phone, during that another conversation will come into play. Another conversation talk you can hear. So that is called as crosstalks. So unwanted or undesired calls gets connected to you in between your own conversation. So this we call as interference. So when this occurs, the communication itself gets failed or lacked. The purpose of that particular call that we have done becomes wasted. Okay. So this occurs in voice channels. This was specifically in the 1G generation, first generation, and the second generation systems. Next is the interference in control channel causes. Okay, first we have seen in the voice channels. Second is the control channels. In control channels, what happens is that the errors will occur in digital signaling, which causes missed calls, blocked calls, or dropped calls. Missed call in the sense, when you try to attend a call, it is being made to you. Before you attend the call, it will get disconnected. Okay, and you make a call to some person. You want to call a person who actually did not block you, will get blocked up. And during the conversation or during the connection itself, your call will get dropped. So these are the effects of interference. Effects of interference. Now let us see the types of interferences. The co-channel interference. Second one is the adjacent channel interference. So this co-channel interference is caused due to cells that you reuse the same frequency set. Same set of frequencies. A everywhere. B everywhere. So that is your co-channel interference due to that. Adjacent channel interference is that it is caused due to the signals that are adjacent in frequencies. For example, 1000 megahertz is there. It is the frequency of one channel. 999 megahertz is the frequency of adjacent channel, and 1001 megahertz is the frequency of the adjacent channel. So if this is the case, interference will definitely occur. So this type of interference is called as adjacent channel interference. Okay, channels having frequency in adjacent to them. Okay, that we call as adjacent channel interference. So, in what are the cases co-channel interference occurs? Or if co-channel interference occurs, what will happen? So, increasing the base station transmitter power to improve radio signal reception will increase the interference to other co-channel cells by the same amount. So, no net improvement will occur. So, separating co-channel cells by some minimum distance to provide sufficient acceleration from propagation of radio signals can be done. But if all cell sizes, transmit powers, and coverage patterns are same, co-channel interference is independent of the transmitted power. So, this is the best way. So, there are two solutions. One is increasing base station transmitter power to improve the radio signal reception. If you do that, it will increase the interference into other co-channel cells by the same amount. There is no use. Another is that separate co-channel cells. You can separate these co-channel cells. That's what A is separated by DF in all the cells. If that can be done, then the co-channel interference is independent of the transmission. It will be independent. So this can be minimized. At what distance this can be done is that it depends upon the D factor. So, which is your frequency reuse. So how do I determine that D? So D is the distance of the distance to the base station of nearest co-channel cell. So A to A, where D should be always R into square root of 3 into N. If the D by R is increased, then spatial separation related to the cell coverage area will improve, and therefore co-channel RF energy will get isolated. Next is that hexagonal shaped structures, Q. Q is the co-channel reuse ratio. D by R is equal to square root of 3 by N. So smaller value of Q provides larger capacity, but it will be higher co-channel interference. So there is a trade-off between capacity and interference. Small Q, that is a small D by R, will make small cluster size with more frequency reuse factor with larger system capacity. Another thing is that if Q is smaller, there will be a small cell separation but increase in CCI. So it should depend upon CCI should be maintained at a normal distance. Co-channel interference. So next is how to calculate signal to noise ratio or the signal to interference ratio. So the signal to interference ratio for a mobile is S by N, S divided by summation I is equal to 1 to I naught II. So that's the desired signal power. II is the interference power from the ith co-channel cell. 1, 2, 3, 4, and it goes on. The average received power at a distance D would be PR is equal to P naught D by D naught whole power minus N. Where P naught is the received power at reference distance D and N is the loss exponent that ranges between 2 to 4. So Di is the distance of the ith interference, the received parameter proportional to Di of minus N. Then you can calculate the signal to interference ratio for the mobile as signal from internet base station and at the edge of the cell, which is R, divided by signals from other base stations, D. So R away by D away. R power minus N divided by summation I is equal to 1 to I naught Di power minus N. Okay. So with only first layer of equidistance interferences, if I take for hexagonal cluster size, which will always have 6 4 channel in the first tier. Okay, 6. So I'm taking 6. So summation I is equal to 1 to I naught into di minus n will become 6. So d by r whole power minus n is d by r whole power n, which is the root of 3 into n the whole power n by 6. So q, the q power n divided by 6 is the signal to noise, signal to interference ratio. Next is the signal to interference ratio for cluster size of n is equal to 7. So the approximation of the exact geometry is shown in this diagram. You can see that 7 is the A, 7 reuse factor. You can see that here 1, 2, 3, 4, 5, 6, 7. And a d by r is present here. The approximate can be given by. So this is the point. So the approximate of a signal ratio is given by S by is equal to r power minus 4 divided by 2 d minus r whole power minus 4 plus 2 d plus r whole power minus 4 plus 2d minus 4. In the case of n is equal to 7. Here this is n is equal to 4. So next is the adjacent channel. Adjacent channel interference. So this interference results from imperfect receiver filters, which allows nearby frequencies to leak into the passband. These can be minimized by careful filtering and channel assignment schemes. The channels are assigned such that frequency separations between channels are maximized. So the distance between the frequency 1 and frequency 2, if it is being maximized, then adjacent channel interference can be minimized. For example, it is given here that by sequentially assigning adjacent bands to different cells, there are totally 832 channels. As an example, given two groups, which is 416 channels each. Out of them, 395 channels are voice, 21 are control. So these 395 are divided into 21 subsets, containing almost 19 channels. Okay, with closest channel 21 channels away. So if n is being used as a use factor, n is used, each cell will use 3 subsets because 21 by 3, so 21 by 7 is 3. So assigned in such a way that each cell is in a 7 channels away. You can see that diagram here. 1, 2, 3, 4, 5, 6, 7. So A is assigned with 1 and 8 neighboring. Okay, 1, 8. B is assigned with 2, 9. C, 5, 12. See the gap between. So here the frequency gap is increased. So 7. You can see that 1 and 1, 8 is neighboring to 7, 14. And neighboring to 3, 10. Neighboring to 6, 13. Neighboring to 4, 11. Neighboring to 9, 2, 9. Neighboring to 5, 12. So this is how frequency planning and channel assignment can be done to avoid adjacent channel interference. So this is an channel allocation for advanced mobile phone system, the first generation systems being deployed. First generation cellular systems. Advanced mobile phone service AMPS channel allocation for A and B side carriers. Okay, 1A, 2A, 3A till 7C. So this is the frequency numbers being used. Okay, as we do to avoid adjacent channel interference. So adjacent channel interference can be minimized only by separating the distance between the frequencies. I can use this frequencies in sequence, but I need to allocate in different fashion. So a fashion like this. You see here, A in A cell itself, 1 is present in here, 2 is present here, but it is separated by 9. You can see that. 1 and 2 is separated in between by 9, ninth frequency. So here 1 and 4 is separated by 11, 6 and 3 by 13, 6 and 1 by 13, 8 and 10 by 3. Whereas 1 and 10 is separated by two different frequencies, 8 and 3. Whereas when you see 10 and 11 is separated by 8, 3. Sorry, 1, 8, 3. So this is what frequency planning is to avoid adjacent channel interference. So any queries in this difference, channel or adjacent channel? Determination of signal to noise ratio, signal to interference ratio. Any queries, type in chat box, because the next topic is entirely different from the interference. I'll give you 2 or 3 minutes time. Any queries, type in chat box, then we'll proceed. Okay. Next topic is trunking. So in this topic, we are going to see the concept of trunking, definitions, the Erlang unit of traffic, rate of service, the types of trunk systems, and the trunking efficiency. So what is this trunking? Most of the cellular systems rely on trunking to accommodate a large number of users in a limited radio spectrum. Okay, then what is this? The trunking allows a large number of users to share relatively small number of channels in a cell by providing access to each other, either in the form of on-demand or in the form of a pool of available channels, either dynamic demand or with the available. Okay, so this trunked radio system is meant for that purpose, particularly where each user is allocated a channel. So for every user, a channel will be present for every call. For a user, for every channel, and for every call, a TRS system is allocated, and depending upon the termination of the call, the already used channel is immediately returned to the pool of available channels. So during the call termination, each user will be allocated per call a TRS, a trunked radio system, and if the call gets terminated, that will return back to the available channel. So some of the key definitions which you need to know during this trunking is that setup time. Setup time is the time required to allocate a radio channel to a requesting user. When a call is being made, then the mobile will send a request to the base station to connect a call. So the time taken to respond by the base station to the mobile or the user to access a radio channel or to access a radio signal is called as setup time. The time required to allocate a radio channel to a requesting user. Next is the blocked call. So call which cannot be completed at the time of request due to congestion or dropped call, called as blocked calls, or it is called as lost call. So when call is in progress, so without the request being by the users, the call gets disconnected due to congestion or traffic is called as blocked call. Next is holding time. The average duration of a typical call means when two mobile users or two users are in conversation, that they are talking to each other or they are conversation with each other. Okay, so that will take some time to make conversation, right from starting of the call to the end of the call. We call it as holding time, which is denoted in H, measured in seconds. Okay, holding time. Next is a request rate. The average number of calls requests per unit time, which is lambda. Number of calls made per unit time. For example, in 60 minutes, you are making some 30 calls. So 30 by 60 is your request rate. Next is the traffic intensity. So the measure of channel time utilization or the average channel occupancy measured in Erlangs, denoted by A, is called as traffic intensity. I'll show you this traffic intensity, how to manipulate. Okay, load is that the trunked radio service traffic intensity across the entire trunked radio system, not service radio system. For the entire trunked radio system, there will be some traffic, so that we call as load. So I had said about this traffic intensity measured in airlines. So this fundamental trunking theory was developed by Erlang, a Danish mathematician. So his name is being given after this. So Erlang is a unit of telecommunication traffic measurement. Erlang represents the continuous use of one voice path. It is used to describe the total traffic volume for 1 hour. So a channel kept busy for 1 hour is defined as having a load of 1 Erlang. Okay, how do we calculate this traffic intensity? Is that the number of calls being made for 1 hour in that entire region determines your traffic. And if a single channel is kept continuously on conversation for 1 hour, okay, so 60 minutes the channel is being kept busy or utilized, that resembles it is 1 Erlang. Okay, for 1 hour the channel is being used continuously without any breaks, it is equivalent to 1 Erlang. So for example, a radio channel that is occupied for 30 minutes, so keep in mind 30 minutes, so 30 minutes during an hour carries 0.5 Erlangs of traffic, means 30 minutes is half an hour, so 1 by 2, so 0.5 Erlangs of traffic. So for every channel, minimum load is considered as 0 Erlang. It's 0% time utilization. Maximum load is 1 Erlang, which is 100% time utilization. So this is what traffic intensity is. So now let us see an example. If a group of 100 users, keep in mind 100 users, makes 30 calls in 1 hour, and each call had an average call duration holding time of 5 minutes. Holding time is that how much each and every call is being making conversation. So that is 5 minutes. Then number of Erlangs can be worked out as such. Okay. The minutes of traffic in the hour can be manipulated by number of calls into duration. Now, how much? There are 30 calls in an hour being made. So how much duration each and every call is existing? It is for 5 minutes. So the minutes of traffic in the hour is 150, which comes from number of calls in a duration, 30 into 5, 150. Okay. So the hours of traffic in the hour, in that one particular hour, how much hours of traffic is present, we have to see. So that is minutes of traffic in the hour divided by 60 minutes. So 150 by 60 gives 2.5. So here is the traffic intensity. So the traffic intensity is 2.5 Erlangs for this example. So this is what traffic intensity is. Measure of channel time utilization or the average channel occupancy is traffic intensity. Any doubts in this? Next is the traffic concepts. So the traffic intensity offered by every user is given as AU. AU by user. So each and every user will give its own traffic intensity, which we had seen just now as an example. So which is equal to the average call arrival multiplied by holding time. Holding time is a service time. Okay. So AU is lambda into H, Erlang's. So it is for every user. Then total offered traffic intensity for the entire system of many users. That TRS, there will be many users. Okay. So for them, it will be A is equal to U into users, number of users into AU, measured in Erlang's. For one user, it is lambda into H. For U users, it is U into AU. Then for each and every channel, we need to find. Okay. So the traffic intensity per channel in a C channel truncated system is AC is equal to AC is per every channel. So AC is equal to U into AU, which is the total traffic intensity for users divided by number of channels. Everything is measured in Erlang's. So this is your traffic concept. Next is the trunking with grade of service. In a trunking radio system, when a particular user requests service and all the available radio channels are already in use, the user is blocked or denied access to the system, as we have discussed earlier. And all conversation in the entire cell is being exhausted. Either the call will get terminated or it gets blocked. So this trunking systems must be designed carefully in order to ensure that there is no likelihood that a user will be blocked or denied access. Why? Because each and every customer or a user is paying his own bills. He does pay for everything what he is purchasing. So the TRS system should ensure that there should be very low probability of chances of blocking or denial access. Or else, if there is a higher probability, the user will terminate that network and he'll go for another network. Okay. So the likelihood is that a call is blocked, or the likelihood is that a call experiences a delayed greater service than a certain queuing time, which we call it as grade of service. So you are using an operator 1, for example, idea. I'm saying as an example. If idea is there, you are making a call within idea to idea, it is getting connected quickly. You'll be using it. And in some cases, when you're calling from idea to BSNL, and the call connection is very much longer than your expected time. So then the grade of service will come into play. Queue will experience. So you may move away from the network of BSNL or from the network of idea. So the network operator should take care of this in designing them. So the grade of service is the measure of ability of a user to access a truncated system during the busiest hour. So measuring of the congestion, which is specified as probability. So the probability of call being blocked depends upon the Erlang systems, Erlang B. So blocked calls cleared or lost call cleared or Erlang B systems has been designed, which is blocked. Erlang B is blocked. The probability of a call being delayed beyond a certain amount of time before granting access is called as Erlang C systems, where we get blocked call delayed or lost call delayed or Erlang systems. So there are two types of grade of services. Erlang B systems, which are meant for blocked calls or lost calls. Next is the Erlang C systems, where the probability of call is being delayed beyond a certain time of limit. Okay. So let us see the blocked call systems or the Erlang. So when a user requests services, when a user requests a service, there is a minimal call setup, and then the user is given immediate access to a channel if any one of the channels is available. If channels are already closed and no new channels are available, call is blocked without access to the system. So the user does not receive service, but is try again later. So that's what you get when you make a calls. Try again later. Try again later. Network is busy, or user is busy. Okay. So all blocked calls are instantaneously returned to the user pool. Blocked call clear systems or Erlang B systems. So the modeling of this BCC systems is based upon the following 7 factors. Okay, the calls are assumed to arrive with a Poisson distribution. There are nearly an infinite number of users, no number of users. Call requests are memoryless, implying that all users, including blocked users, may request a channel at any time. So all free channels are fully available for servicing calls until all channels are occupied. So the probability of a user occupying a channel, which we call as a service time, is exponentially distributed, or longer calls are less likely to happen. So there would be finite number of channels available in the trunking pool, or the inter-arrival times of call requests are independent to each other. So this is how do we model the Erlang B systems. So the modeling is given by this formula. Blocked call is equal to AC by C divided by summation k is equal to 0 to C AK divided by K. K factorial. K factorial. Where C is the number of trunked channels offered by the trunk radio system, A is the total offered traffic. So as we are defining trunking. So this is the Erlang B blocked. Number of trunked channels is in C. Traffic intensity in Erlangs varies from 0 to 100. Erlang B chart showing the probability of blocking as functions of the number of channels and traffic intensity in Erlangs. So the probability of blocking will be in this fashion in Erlang B. So an example of the capacity of Erlang B system, depending upon the number of channels. If channels is 2, with the capacity of Erlangs for grade of service 0.01, for 2 channels it is 0.153, for 0.005 it is 0.105, and it goes on. You can see the table which is referred from this. Erlang B trunking and its grade of service. Next is the BCD, which is Erlang C. So here the call when a user makes a call, the call is being delayed beyond a certain level. So queues are used to hold call requests that are initially blocked. So when a user attempts a call and the channel is not immediately available, the call request may be delayed until a channel becomes available. So the mathematical modeling of such systems is done by Erlang C formula or the Erlang C model. So this is also similar to Erlang B. Additionally, it has a queue of infinite length. So that is what it does. In addition to Erlang B, if a queue is added of infinite length, it becomes Erlang C. So additionally, if offered call cannot be assigned a channel, it is placed in a queue of infinite length. So each call is then serviced in the order of its arrival, so depending upon the time. So Erlang C can be calculated by this formula: PR of delay greater than 0, AC divided by AC plus C factorial 1 minus A by C, C minus 1 summation K is equal to 0, C minus 1 K divided by K factorial. So this Erlang C formula gives the likelihood of a call not having immediate access, which is delayed access. So Erlang C is chart. Erlang C is chart showing the probability of a call being delayed as a function of number of channels and traffic intensity in Erlangs. So the modeling of this block clear delay or Erlang C block call delayed. So the probability that any caller is delayed in queue for a wait time is greater than the t seconds, which is given as rate of service of a blocked call delay systems. So the probability of a call getting delayed for any period of time greater than zero becomes your BCD call or Erlang C call. So that is a mathematical formula for that, which we have seen here. Next is the trunking efficiency. Trunking efficiency. So, trunking efficiency is a measure of the number of users that can be offered a particular grade of service with particular configuration of fixed channels. The way in which channels are grouped can substantially alter the number of users handled by trunked system. So let us see an example. So there are 10 trunked channels at a grade of service of 0.01 supporting 4.46 Erlangs, where two groups of 5 trunked channels can support 2 cross 1.36, which is 2.72 Erlangs of traffic. So these 10 trunked channels can offer 60% more traffic at a specific GOS than 2 5-channel trunks. Okay. If you use 2 5-channel trunks, the Erlang is 2.72. Whereas when you use 10 trunk channels, it gives 4.46 Erlangs. Means that more usage of the available channel can be done more efficiently. It is the same trunking of Erlang B. Suppose, let me check it. Yes. B trunking. Yeah, this is the same Erlang trunking of GYS showing the capacity of Erlang systems. If the number of channels increases, you can see the capacity also increases for different GYS 0.01 till 0.001. Okay. Next is improving capacity. Next topic. So as the demand for services increases, system designers have to provide more channel per unit coverage area. Why? Because every day the number of users is not the same. It is increasing. The number of users increases for cell phones or mobile phones. The available channels will not be sufficient to accommodate more and more users which are growing. So the system designers have to provide more channels for every unit coverage. So for this, some of the techniques being used for improving capacity is cell splitting, cell sectoring, and microcell zone. Since I couldn't find any queries in the chat box, I proceed on to the next topic, which is improving capacity. So as the more number of users are being added up to the existing network or existing TRS, so area of coverage should be increased. So some of the techniques to improve that is cell splitting, cell sectoring, microcell zoning. So let us see what is this cell splitting is. Cell splitting increases the number of base stations being deployed and allows an orderly growth of the cellular system slowly. Cell sectoring is that it uses directional antennas to further control the interferences being caused. So let us see how it occurs also. Third one is the microcell zoning. The microcell zoning distributes the coverage of a cell and extends the cell boundary to hard to reach areas. So just like the umbrella cell concept. So let us see cell splitting. Cell splitting is the process of subdividing a congested cell into smaller cells. A larger cell will be divided into smaller cells depending upon the congestion. So by their own base station, keeping the base station as common, and a corresponding reduction in antenna height and corresponding reduction in transmit power. So the cell splitting reduces cell size, and thus in result more number of cells have to be used. So that depends upon the factor again, Q is equal to D by R, which we had seen. For the new cells to be smaller in size, the transmit power of the cells must be reduced. So as we discussed, increase for faster movers, antenna height should be higher. For slow movers, antenna height should be lower. So if there is more traffic, use faster, or the height of the antenna should be higher, and if it is slow, you can use the antenna which is having lower heights. These are the cell splitting. You can see that cells are split to add channels with no new spectrum usage. Without the need of additional spectrum, we split it into small cells. So we have the same cells. You can see that C, G, E, F, and it goes on. So this is entire cell. This is entire cell. So now you see that in between there is 3 cells. Okay, these 3 cells, here there is more traffic. There are more number of users in this particular place. So then we can, with the same base station, we can divide this larger cell into smaller cells. Okay, you can see that smaller cell, smaller cell, smaller cell, without much utilization of another spectrum. Okay, so inside this we have F, E, B, E. This frequency is going on. So inside this you can create another frequency which is not having the same frequency. Okay, D and F doesn't have same frequency, C and E doesn't have same frequency, E and D not same frequency, D and A not same frequency, C and B not same frequency. Accordingly we can design. Okay, this we call as cell splitting. So in cell splitting, the issue that we get is that only power issues due to that. Suppose the cell of radius of new cells is reduced by half, then the transmitted power for these new cells will be at older boundary will be PT1 into R power minus N, whereas at new boundary cell it will be PT2 R by 2 power minus N, because it is being reduced by half. So 1 by 2 of that. Okay, where PT1 and PT2 are the transmitted powers of the larger and smaller base cells, and N is the path loss. So PT2 will be equal to half of PT1, because the cell radius is being reduced by half. One cell is being converted into 2 cells. by reducing its cell radius by half of it. So then the power transmitted will also being get half in that way. So if you take n is equal to 3, the received powers will be equal to each other. So PT2 will be equal to PT1 divided by 8. Okay. So in other words, you can say that the transmitted power must be reduced by 9 decibels in order to fill the original coverage area while maintaining the signal to interference requirements. So to have the good signal to interference requirement, the transmitted power must be reduced by 9 decibels, 9 dB. So this is an illustration of a cell splitting in 3x3 centered around a base station. So we have a base station. A is the base station being provided. So 3x3. So 3x3. So again it is being merged. The DC, B, G, F, E inside it. Okay. If you see this in a 3-dimensional view, it will be easier to understand. Okay, see that this is a cell. So this is a cell where I'm showing in mouse. This is a cell. This is a cell. This is a cell. This is a cell. Each and every cell is separated by, is being split up. Okay, each cell is being split up. So then, with different frequencies, okay, on different channels. So this cross-sectional area is 3x3 center. Okay, 3 cells together. So in practice, not all the cells are split at the same time. Okay, hence different size cells will exist simultaneously. So depending upon the requirement only, the cell will be split up. So depending upon the time, the cell size will vary. So in such a situations, special care has to be taken to keep the distance between core channels cells at the required minimum, and the channel assignments will become more complicated as compared to normal. So to overcome this handoff problem, channels in the old cell must be broken down into 2 channel groups, one for smaller, another for larger. So the larger cell will be dedicated for high-speed traffic so that handoff occurs less frequently. At smaller group, the power will be having less channels, and larger power group will have number of channels that is equal to them. This is how cell splitting takes place. So the same umbrella concept which I had shown you. Okay, cell splitting. Umbrella concept, larger base station antenna and smaller base station antenna inside a cell. So this is a cell splitting representation for urban areas and for rural areas. Larger cells are used for rural areas because there will be only lesser number of persons being using mobile phones, and the traffic will be very less. Whereas in urban, there will be more number of people, more number of mobiles, more number of usage, more traffic. So smaller cells for urban areas. So this is your classification. You can see, and classification along the D11 CFR river in US. where how the cells are being split up in diagrammatic representation. Along the river, this is your river valley. Along the river valley, so the cells are split at a larger in this. This indicates rural. Here it is small, 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 small. More number of cells are present. So this indicates your urban. Okay, I think